Swayam Prabha. Digital India. Educated India.
Code elimination. In what way do we use it? Observe that here exit of N5, nothing is live at the exit of N5, right, and yet we are defining this variable A. It means that this assignment is redundant. This assignment can be removed as an instance of dead code elimination, right. So, if we change this program and remove this assignment, now the program has changed. We have to recompute the liveness analysis, okay. And it is easy to see now that here C that was live, because this assignment has gone, now C will not be live at N5, right. So, therefore, we will get liveness result something like this. Now, we do not have C as live anywhere. That was the only instance of C that was in the earlier solution. C was live everywhere, now C is not live. Okay. Now, we can further do it. We observe once again that the out of N5 is still empty, and we are computing T1 equal to A plus B. This value of T1 is not required. So, we can delete this statement as well, and we can once again recompute the value, and this is the result that we get. Okay. If we have time, we would see an analysis which does it as a part of the same analysis. Right now, what are we doing? We do liveness analysis, then we do transformation of dead code elimination, once again we do liveness analysis, once again we do transformation of dead code elimination, keep doing it until things keep changing. But there is another analysis called strongly live variables analysis, which can do it in the same instance of analysis. Okay. We will see that tomorrow. Okay. So, this was liveness analysis, and now we have here at N1 we have A and N are live, B and C are not required. So, we can get rid of those two assignments as well. So, this is how we can use liveness analysis. So, let us make some observations. Now, let us try to generalize. We have seen a concrete example. Let us try to ask some general questions and see whether we can make sense of some general, we can find some general patterns. So, what does data flow analysis involve? So, a data flow analysis involves, doing data flow analysis involves these three things: define the analysis, formulate the analysis, and perform the analysis. These are the three things that have to be done. And in order to define the analysis, we define the properties of execution paths. In order to formulate the analysis, we define data flow equations, which are linear simultaneous equations on sets rather than numbers. Later, we will generalize the domain of values. Performing analysis, solve data flow equations for the given program flow graph. And there are many unanswered questions. What should be the initial value? How do we guarantee termination? What is the complexity of this algorithm? What are the properties of these solutions? We will talk about them as we go along, right. We will try to answer all of these for liveness analysis at least, if not in the general case. Yeah. Which one? This one?
How surely we can remove the C equal to T1 plus A?
Which statement are you talking about? This one or this? This one, A is equal to T1 plus C. So, his question is, how can we remove A is equal to T1 plus C? Would anyone like to answer that question? Value of A is not required any further. This is the program that we have, entire program. Where is it required? Show me. There is no other statement. This is the program. This is the entire program. You cannot perform analysis until you look at the entire program.
Means we cannot remove just by seeing the out any. So we have to look the what is inside the block also.
So, out will tell you what is happening at the end of this block. Then you have to look within the block and find out whether there is any use. So, for example, you cannot remove T1 plus this because there is a use of T1. So, you will have to examine within the block. Now, within the block these are the only 3 statements, there is no use of A, and therefore, we can see, remember in the morning we talked about last occurrence. So, you will always begin by applying this out information to the last occurrence within the basic block, and the last statement, last assignment statement within the basic block is this. So, you see that A is not used, this statement below this does not use A. So, therefore, you can delete this assignment, right. Okay. So, this is what we saw. So, how do we, so here is a small digression on iterative solution of linear simultaneous equations. So, these are simultaneous equations represented in the form of a product of a matrix of coefficients A with the vector of unknowns, and we write it as Ax is equal to B. The idea is to start with approximate values and compute values repeatedly from old values. This is an iterative solution. There are other ways of solving it, but let us look at this method. There are 2 classical methods, one is a Gauss-Seidel method and the other is a Jacobi method, and they are really very old method, 1823 and 1845. Okay. So, here is a simple example of Gauss-Seidel method. So, we know, so this is a very simplistic example, x, y, z, all of them are 16. So, 4w is equal to x, y plus 32. So, we know the solution is 16, it is easy for us to look at the solution, but the question is how do we find it out iteratively. So, we rewrite the equations to define w, x, y and z. So, w is equal to this. So, we define everything, we divide everything by 4 and we get this. Okay. Now, we assume some initial values w0, x0, y0 and z0, and then we compute wi, xi and yi and zi within some margin of error. We say if the difference with the previous computation is less than this, then we will stop, otherwise we will continue. So, let us say we begin with this is our equation, our initial values are 24, we know the solution is 16, but let us start with something as deviant from it as 24, and let us say our error margin is that the difference between 2 successive values of w should be less than 0.35. For if the difference is less than 0.35, then we are happy with the solution. Okay. So, in the first iteration we plug in these values 24 and recompute this. So, 24 into 0.25, that is 24 divided by 4 gives us 6, this gives us 6. So, everywhere, so this block gives us 6 because we started with 24 and we get a solution 20. Now, we find out the difference between 24 and 20 is 4, which is greater than 0.35. So, we must compute it again, right. So, now we plug in this value 20. Now, 20 will be divided by 4. So, that becomes now 5. So, this block now becomes 5 plus 8 and now we get 18. Now, the difference between 2 successive values 20 and 18 is still 2, which is larger than 0.35. So, we must recompute, and when we recompute we start with 18 and when we divide 18 by 4 we get this value 4.5. Now, we get the result as 17, right. The difference is still larger than 0.35. So, we recompute, we plug in that value and we get this 16.5. The difference is 0.5, still larger than 0.35. So, now we compute the 16.25. So, we use this value, we get this and we get 16.25 and the difference is 0.25, which is smaller than this. So, we say this is our solution. Of course, we can get more precise solution by keeping the error margin small, right. So, and we can keep recomputing. So, this is essentially the Gauss-Seidel method of iterative solution. Observe here that we have a use of w here and this W. So, we have used the value of W here as 24, whereas this W has already been computed as 20. So, it would have been possible for us to use the values computed in the same iteration rather than compute taking it from the previous iteration, and that is essentially Jacobi's method. So, how do we use Jacobi's method over this? So, we once again start with this, and now things start becoming different. Here we, for the value of W, we use the value of W computed in this iteration, right. In the previous method we used value of W from here. So, the idea is, one idea is compute all values by using values in the previous iteration versus compute all values by using values in the same iteration wherever possible. As you would expect, this should be a more efficient method, right. So, we compute this. So, we use 5 which was computed, we use 20 which was computed here. So, we compute y, and because Z uses W, so we use W here, and Z also uses x which has been computed. So, we get these values, and now the difference is still 0.35, larger than 0.35. So, we recompute and we recompute. So, now we get these values. At every stage we keep using the values of y and W and x computed in the same iteration, and now the values start differing. Earlier values were same. Okay. Now, we once again recompute and we get some other values, and in fourth iteration we get. Note that these values are different here, they are not identical, but they are still within our the error of margin. This has taken 4 iterations, whereas the Gauss-Seidel method had taken 5 iterations. That is because we are reusing the values. So, when we do data flow analysis, what we are essentially doing is, we use this method called round robin iteration. We visit, this is the simplest method, we visit the nodes in a fixed order, and that order could be decided by the direction of data flow. For example, for liveness analysis we visit in the backward direction. For some other analysis such as available expressions analysis, which we will see as our next example, we will visit in the forward direction. So, we use this round robin method, essentially Jacobi method. We use Jacobi method, we reuse the values wherever possible, right. Unknowns are the data flow variables in I and out I. Domain of values is not numbers. Computation in a fixed order, either forward or we formally call it reverse post order, or backward or post order traversal over the control flow graph. So, this is the method of performing data flow analysis, a method that we are using. Of course, there are more efficient methods such as work list methods, but then as I said, it will not be possible for us to cover it in these 2 days. Okay, so here is another tutorial. Draw the control flow graph and performing liveness analysis. We will perhaps not wait here. There are several other tutorial problems that I will give to you. So, here is the control flow graph that we, and so I think we will skip this. So, all this tutorial, the slides will be given to you at the end of this session. You can go over these problems, and if you have any questions you can ask me. And now let us answer some questions. Stare at this program for a while and try to answer this question. Is A live at the exit of N5, which is this, at the end of iteration 1? I am not talking about finally. When you perform the first iteration, do you expect it to be live? Now, we have fixed our method. Now, you are not guessing. You start in this order, you first compute N6, then you compute N5, then N4, N3, N2, N1. That is a fixed this thing, and it is a Jacobi method. So, when you compute N5, you use the value from N6 if you have to. When you compute N4, you use the value of N5 and so on. So, in the first iteration, do you expect A to be live at the entry, at the exit of N5? Yes or no? And how will you get it live here? at the end of the first iteration? In the first iteration, out of n5 is equal to in of n2. What is the initial value of in of n2? No, initial value. What is the initial value? What is the initial value that we are choosing for liveness analysis? Empty set. So, you will not find A live at the A will become live at the exit of n5 as the effect of this loop in a subsequent iteration, right? Do you all get it? Is A live at the exit of n5 at the end of iteration 2? Yes, of course, we just now talked about it, right? A will be live, and why? Why would it be live? Because of which path will A be live? So, give me a path starting at n5 that uses A. N5, N5, N2 and then N6, yes. Any other path? N3? No, not N4. N4 it gets killed here. So, N3, N5, right. These are the two paths because of which A is live at the exit of N5, right. So, show an execution path. So, we already talked about it at the exit of N5. Show an execution path along which A is live at the exit of N3. A simple path N3, N5 and so on, right. So, this is okay. Show an execution path along which A is not live at the exit of N3. N3, N4, yes, this path that goes through this, right. Okay, very good. So, now you can attach some intuitions to it. So, again there are tutorial problems, and so this is a converse problem. You are given a program and you are supposed to write a control flow graph. Here you are given a control flow graph and you are supposed to write a program for it, and you are not allowed to use gotos. So, you had one of the tutorial problems, I think. So, this is, so I will skip this again. Okay, so maybe I will skip this as well. What time is it? It is already 3:20, maybe I will skip this as well. You can go through these slides and find out the answers. Okay. Now, what should be the initial value of the internal nodes? So, we said boundary info is fixed by something else, and we will look at the effect of BI for the next analysis, which is available expressions analysis. But initial value for live variables analysis, we chose it to be empty set, okay, because the confluence is union. Confluence is the way the values are merged, right. And in this case, we are saying out of a node is, observe this, out of a node is a union of n of its successors. So, we are merging values using union, and we want to use the identity element of our confluence operation. So, what is the identity of union? Identity of multiplication is 1, identity of addition is 0. What is identity of union? Phi, empty set. So, you start with something that does not over approximate the union, that is the idea. So, therefore, you use identity element. So, we use empty set. So, this is a workable definition. We begin with empty set and let the sets at each program point grow. So, we start with empty set, and when we recompute the set, we are not going to get anything less than an empty set. So, sets can only grow, right. So, in liveness analysis, we begin with empty sets and sets only grow, okay. A revisit to a program point may consider a new execution path, more variables may be found to be live, but the important point is a variable found to be live earlier does not become dead. If at any program point, if I discover in some iteration that A is live, it will remain live always. It will never, in a subsequent iteration, it will never be declared as dead. Can you all see that? Can you all see that? The reason is we are starting with an empty set. So, we are simply adding and we are taking union, right. So, the sets can only grow. So, what does that mean? So, let's so which means that this guarantees termination. Okay. Now, why should we use empty set versus something else? So, let us look at this program. Here what do we expect to be live? Here nothing is live, nothing is live. Here what is live? B is live, here B is live, and here B is live, right. A is not live anywhere, right. So, we start with empty set and we compute our liveness analysis. This is empty, empty, empty. Initially, it is going to be empty because we started with this. So, out of this will be in of this. So, it will be empty. So, then we say B is live, then we say B is live and nothing is live. Now, we recompute the values. So, we once again begin with this and we have B. Now, this B becomes live. This is the solution that we get with the initialization empty set. Instead, supposing we use this initialization AB, we use universal set as our initialization. What do we get? What is the final solution that we will get? Can you compute it and let me know? A will always be live. A, B, both of them will be always live. So, our solution is, we begin with this is empty set initially, this is A B because that was initialization, this is A B, because A is live here it is not killed. So, A is live, this is A B and this is A B, and now in the next iteration we find that this remains same. So, A is spuriously marked as live, right. If we started with initialization something other than empty set, it is possible that we might get an over approximated result. So, choice of initialization affects the quality of the solution that we get. Okay. So, let us now come back to soundness and precision of live variables analysis. So, consider dead code elimination based on liveness information. So, if we spuriously include a live non-live variable. So, for example, here in this block J, Y is live, but we mark X also as live, let us say by mistake. What will go wrong? What will go wrong is you will not be able to delete this assignment as dead code elimination, but that is a harmless error. It is not going to change the semantics of the program at all, it does not matter, right. So, a dead assignment may not be eliminated, solution is sound, but is imprecise. It is imprecise because we are missing some opportunity of optimization, right. Consider the opposite case where X and Y both are live, but we forget to mark X as live, we only say Y is live. Now, what is going to happen? As a consequence of this, we might end up doing dead code elimination. Okay. As useful assignment may be eliminated, the solution is unsound, right. We might get into trouble because of this. Okay. So, in general, given L2, which is a superset of L1 representing liveness information, using L2 in place of L1 is sound. If L1 is sound, L2 is sound. Can you all see that? If L1 is sound, meaning it has every variable that must be declared as live, and L2 is a superset of L1. So, L2 definitely has every variable, it might have more variables. So, every variable that must be declared as live, and therefore, L2 is also sound, right. Using L1 in place of L2, however, may not be sound. because if L1 is a subset and L2 contains all variables that are live, it is possible that L1 might exclude that variable, right. So, that tells us soundness and precision. The smallest set of all live variables is most precise. This is another reason why we start with empty set as our initialization. So, as the previous example, previous slide showed, we could start with A B as marked as. So, in this example, this is a sound result, but it is not a precise result. Okay. And if we declare all variables live at every program point, it will be trivially sound. The solution is trivially sound and the solution is profoundly useless, right. Okay. So, since liveness sets grow, confluence is union, we choose empty set as the initial conservative value. You start with the smallest set and you want the smallest, you want to let it grow only as much as is required to achieve soundness and no more. You know, we talked about it in the morning. So, therefore, we start with the smallest set, which is empty set, and let it grow as much as is required and no more, right. That tells us about soundness and precision of liveness analysis. What about termination, convergence and complexity? For live variables analysis, the set of all variables is finite. The confluence operation is union, hence the sets associated with a data flow variable can only grow. A critical component of this analysis is that the kill information is constant. So, if we kill, in every iteration we are going to kill essentially the same set of variables. So, if the incoming set of variables is larger and we are killing the same set of variables, the outgoing set of variables will be larger. So, sets can only grow. We start with empty set and maximum what will happen? We will reach the set of all variables. Because this is finite, liveness analysis must terminate. Termination is guaranteed. We should not have any doubt in our mind whether we will continue to iterate forever for this analysis. There could be some other analysis which is ill designed and you could keep iterating over it again and again. Since the initial value is empty set, live variables analysis converges on the smallest set. So, termination, what does it converge on? That we have decided. How many iterations do we need for reaching the convergence? Well, this is an interesting question which I will not be able to answer now, and I am not saying because I do not know the answer, I know the answer, but I need much more time than we have here, but there is a way of answering that question, a very interesting way of answering that question. I will perhaps touch upon it sometime tomorrow. Going beyond liveness analysis, do the sets always grow for other data flow frameworks? What is the complexity of round robin analysis for other data flow analysis? These are interesting questions that you have to come to IITB to get those answers, will not be able to give those answers right now. Okay. So, let us now look at two. So, we talked about conservative nature, we talked about imprecision, we talked about soundness. Let us look at where does this imprecision come from? Why is it that certain things are unavoidable? So, here is an example. This absolute n returns the absolute value of n. Is y live on entry to block B2? Yes or no? No? Okay. So, we have an answer which says y is not live at entry to block B2. Anyone who thinks it is live? Yes? Yes? Why? Why is it live? Yes, but what property of analysis makes it live? So, the interesting thing is by the execution semantics no, because this execution path is an infeasible execution path, right. Absolute value of x can never be less than 0, right, and this is where y is being used. So, by program semantics y is not live, but we are unable to, we are not executing the program, we are doing static analysis, right. So, we assume every path, every branch outcome is possible, okay, and therefore, we ignore whether this is true branch or false branch, and therefore, because of this conservative assumption, a compiler makes y as live, right. Our analysis concludes that y is live on entry to block B2, but that is okay because it is sound, although it is imprecise, right. Okay. About this, is B live on entry of to block B2? Variable B is used here. Is it live here? Yes? No. Okay. Anyone who thinks yes? Little louder, please.
Semantically it's not live because if x is less than 0, the value of x will be changed.
Yes, semantically it is not live because if x is less than 0, the value of x has not changed. So, this condition branch outcome will remain the same, right. So, this is another example of an infeasible path, but our analysis will assume that look, sorry boss, kuch nahi kar sakte, we will have to mark B as live, okay. This is what the standard literature says, but there is a way of avoiding this. My PhD student Komal published a paper in Compiler Construction Conference this year, which shows how we can avoid these problems. So, he takes any general data flow framework and creates another, lifts it to a level where all infeasible paths are removed and we get a more precise solution. So, there is a way of doing it, it is possible for us to do it, but as far as standard literature is concerned, the conservative nature of analysis says that look, we cannot do it, right. Of course, there is a cost to pay, your algorithm becomes more inefficient and less scalable if you did that. So, you can get more precise results. Okay. So, again the same reason, so we have seen. So, the important point is our analysis is path insensitive. We are not keeping different information for different control flow paths, because the number of control flow paths is exponentially large and in the presence of cycles it is infinite. And Komal's research essentially shows how this combinatorial explosion need not affect us, how we can still make do with smaller distinctions and not keep combinatorially large values distinct for each path. So, how do we do path sensitive analysis? So, his paper is titled partially path sensitive analysis. Of course, you can't do fully path sensitive analysis, again the data flow analysis is undecidable. So, by default we are doing path insensitive analysis, right. So, let us skip this. So, we assume that all paths are potentially executable, our analysis is path insensitive. A data flow information at a program point P is path insensitive, meaning information at P is merged along all paths reaching P. Okay. Data flow information reaching P is computed path insensitively. So, let us skip this. The other things that are called context sensitivity and flows insensitivity, context insensitivity, which is something that we will not be able to cover here. You have to come to IIT Bombay to study all these things. Very interesting questions, very interesting issues, interesting solutions to these problems by my PhD students, and nice things, but some good things have to be kept out of life when you have only 2 days to live. So, that is what. right. So, we will not be able to look at this. So, again soundness, that proof we will not be able to do it here. So, before we go to the next analysis, any questions about liveness analysis?